For the first lecture, well, I'll fit it in now, so I hope we'll be done by 7:30. And what I plan doing is, this loop series, we'll get back to it, but not today. We'll get back to it on Saturday, and this lecture 5 will be basically about specialized graphical models, which you can analyze with the loop series and other techniques, other tricks. And by the way, lecture 6 will be mainly discussing very briefly, and you see this list is longer, problems which to a degree solve, but not completely, and actually there are quite a lot of open problems. So it will be more focused on open problems, and it will be an attempt to welcome you into basically working on it by yourself and welcoming into this project stage. But for today, what I plan doing, I plan telling you about some other complementary techniques which are not about loop series and loop calculus and loop transformations, but somehow useful and have their own appeal, so to a degree they are complementary. And I'll not be going into nitty-gritty details of those techniques, so it will be some exposition, but only to a degree, kind of setting up problem and maybe sharing with you main ideas the way I see it. For that matter, all those subjects, they also would be very good if somebody will pick up one of them and basically will do more extended report to all of us. And we will discuss how we'll be doing in this project period. You see there is a long list. Probably will be a little bit longer for the first two, and actually for the first self-avoiding tree approach. Then cumulant expansion, generalized belief propagation will be rather brief, and graph covers will be only a statement of what is that and what you can get, not much of the details. So all those methods, they are very young. So all this is this generalized belief propagation, which actually kind of, this paper, now famous paper, it has more than close to 2,000 citation of Yedidi Freeman Weiss, and I already mentioned it. It's from 2001. So cumulant expansion is 2008, self-avoiding tree is 2006, graph covers is started 2005, but main contribution 2010, so it's all very, very hot. Okay, so so we'll get back to loop series, but not today. And now, so I also will try to explain them in a kind of informal way, and more like illustrating, not proving, but to a degree, these illustrations carries ideas of proof. So Dror Weitz is the author. So it's called self-avoiding tree for reason which will become clear immediately. Actually, it's also an interesting story. So Dror was postdoc, I think, at Rutgers, and he had this paper which immediately attracted a lot of attention. There are nice, beautiful proofs which followed, and only when and instead of following up on that, he completely dropped and he returned back to Israel. He's from Israel and he's working on some Wall Street type of job. I don't know what he's doing, but it's kind of pity because it's a really beautiful work. So just to maybe illustrate immediately and give you some ideas or arguments why it works and why it is so. It's the exact method, and it's about computing marginal probability, and representation which we're using here is actually one which this graphical model discussed. I think it can be generalized to many other graphical models, but this particular one is this Ising model type. So you have variables on vertices, factors, functions are on edges. And it may be Ising model or it may be independent set model. So there are a number of models which are covered by that. And that's how he introduced it, but there are certainly generalizations. But let me explain how it works in this case. So model is written in here, so it's, in the case of Ising model, this f is exponent minus this sigma I, sigma j quadratic term. But I mean, in general, let's keep it this way. And it will be, I think he explained it for binary case, and also we'll be discussing binary. So what is the problem? The problem is to compute marginal probability at a node. So I pick one node, so that's where my variable sits. Well, this is called a spin. And I want to compute probability of this variable to be plus or probability of this variable to be minus. That's one of those problems which we discuss as important. And there, of course, in the same class as computation of partition function. In a binary case, kind of equivalently, you may want to compute not probability at I to be plus or probability minus, but just the ratio of the two. Because sum of those values is 1, so obviously if you know ratio, you know each of them. And remarkable, absolutely remarkable statement is that instead of doing it at this graph, for example, you can do it at this graph, which is a tree. And this tree is called self-avoiding tree. And how you construct this tree? Well, you construct it doing walk through the graph and doing it in a self-avoiding way. So you start from here, 1, you go to 2, you go to 4, you go to 3, and if you return to 2, you finished, you're done, right? That will be one particular pass in here. So for example, 1, 2, 4, 3, 1. 1, 2, 4, 3, 1. And it's direct to check that all those passes are forming this tree. So now, in addition to that, construction is such that you put values at those end nodes, at the leaves of the trees. And which value, particular value you put, plus, minus, there is some prescription, there is some concrete rule, which, well, I guess I'll explain later on. But those values, so those values at the leaves are fixed. And a remarkable statement is that this object computed for this model is equivalent to the same object but computed for over this tree. And by the way, immediately, well, you may ask, well, tree computations are easy, so you are done. The catch is that this tree, well, it's easy to see that tree will be large, right? So for this relatively small graph, it's not that long, but in general, it will be exponential in size. But it's a finite tree, it's not infinite tree. And, well, there is also some relation to belief propagation, which I actually kind of forgot to emphasize, but maybe somebody will want to pick it as a subject. There is an interpretation of belief, well, maybe we'll discuss it on Saturday. There is interpretation of belief propagation in terms of a computation, so-called computational tree. And computational tree is infinite tree, but this is finite. So it's a kind of part of a computational tree. Yeah, so here is, when I first time saw it, first of all I was very surprised, I didn't believe it's correct. Then I thought that it should be related to our loop calculus, and neither of those statements appears to be correct. So it is right, so he certainly did everything correctly, but I don't see direct connection. That's actually one interesting change. And of course it's quite different, because here what I'm doing, I'm not doing computation with the same graph. I'm modifying graph. I'm not changing factors, but right. And yeah, important thing is that when I was constructing the self-avoiding tree, or drawer was constructing, well, there are repetitive nodes, right? Node 4, node 4. Well, there are many replicas on node 4, of course. Factors are the same in those nodes, but of course you should think of them as the same factor as functions, but of course variables are completely independent. Okay, I hope you already kind of puzzled, surprised. So let's see why it works. And well, that's my way to explain it, and it's actually rather straightforward. So it's a set of transformations, set of graph transformations, and they're roughly split in, I mean, not roughly, they're split in 3 different types of transformations, and I put them in a pictorial way. So let me just walk you through that. So maybe you don't see details yet, but you can kind of well. So I'll be focusing on this object. Draw introduce it for this object. I'll be focusing on this object, right? So there is this plus and minus. And when I take this graph, I put plus or minus in here, right? Well, I have a ratio, plus or minus. I'm getting this type of structure. Well, in this particular case, there are only 2 edges, but in general, there are a number of edges emanating. So let me magnify, and then we'll see. So that's what I have. Plus, minus, and then when I put this block, it doesn't matter what I have in there. So some graph. And let me do transformation. And transformation will bring me from here to there, and that will be a kind of significant portion of this construction. So I'm kind of opening up, at least those small loops. You see, so I don't have loops, I have openings in here. So whatever is blue still remain, I mean, looping possibly. I don't resolve it in here. But at least those small loops I'm getting it. And let's see what I'm doing, or what drawer was doing. Yeah, so it's my interpretation of this work. So first of all, well, since this variable is fixed, it's plus. It's the same as basically connecting, well, basically opening it up, right? So I'm not doing summation with this variable. I just introduce 3 replicas and put 3 pluses. Right? I can do that. The same in here. And then I start multiplying and dividing by the same objects. Okay, let's see. So those 2 are basically original. But now 1 to 3 minus plus plus, the same here, right? So multiply, divide. Still innocent, of course, assuming that they're not 0. And then I start kind of reshuffle, rearrange. So I pick this 1 plus, right? 1 plus, and I put those up. The same here. So I pick now 2, this plus, open it up, right? So it's just direct transformation. And now I can merge them because again they are pluses and it's still fixed. And that's where I arrived. So I started from a ratio of this type of contribution and I got those 2. And kind of similar, well, will be a little bit different transformation, but that's more or less a gist of how you deal with the structures. Another well will be basically two more different structures which are important to pull it all together and basically get to this self-avoiding tree. So imagine that I have this situation. I have the same ratio of the 2 terms, the same structures in here, but something different. And here I didn't specify what exactly is different. So it's also kind of some loopy graph potentially and some summation, but no open edges. And those A and B are potentially different. And now, okay, so what I'm doing, I'm again duplicating. I'm assuming, so basically over here, over this variable I do summation, right? And it's why I put flux. And then, right, so I basically have 2 terms here, 2 terms here, and then I multiply and divide by the same terms. And okay, so maybe let me just jump to the end. So that's where I start from, and let's see where will I get, and that's where will I get. maybe let me return back. So, and again, my goal is to open up those small loops. And that's more or less what I'm saying I achieve. So let me not walk you through that, but it's clear, it's roughly clear what kind of transformations I'm doing. I mean, idea of transformations. It probably will be much easier if you'll just check yourself later on. And of course, for me, it's the easiest way to see it. In the drawer paper, there are no graphs, and there are very dense, formulas. But those all algebraic formulas, and I think it's a kind of clean interpretation. And there is this another piece which I think is important. But in any case, so altogether, when you combine all those things, so that's what you get. You get from this type of graph to self-avoiding tree, and it's very straightforward, geometric, algebraic, whatever way you follow. So that's nice. Actually, in the paper, in this Drawer-White's paper, if you look at it, this construction is only part of a proof of certain properties of market chain. So it was auxiliary, but I think by itself that's probably most remarkable. Part of all of that. But he invented it for some other purposes, which I'm not covering today. And so this is a link, it's certainly a very good subject for project, and we probably can discuss it in more details. And there are actually a number of follow-up papers which are also remarkable by themselves. And I'm not sure who was first, because all of that happens more or less like here. But of course, it was initiated by this drawer paper. So Andrea Montanari and Kirill Miasson, and the first author I don't really know him. They basically take it as okay. So the self-avoiding tree is huge, as I said, but hopefully when you go further down a tree, you expect least and least dependence on when you're deep in the tree. That's so-called decay of correlation assumption. And if decay, there is this whole discussion in the literature of under which condition you have this decay of correlations. You really can ignore. This discussion is actually started in the context of this computational tree, not self-avoiding tree. But very naturally they extended it to this case, and suggestion was truncate, basically cut it. So I don't think there are many proofs, which is very atypical for Andrea, but in any case, so they experimented, and it's an interesting paper. So David Gamarnik, with his former student, Dima Katz, they play, they basically, they also develop some truncation scheme, and it's clear from the title, right? So it's basically they view this Drawer-White's approach as a fully polynomial time approximate scheme. This term, I don't know, you probably already, some of you maybe heard of it. So it's basically when you target developing approximation for counting for partition function, but there is approximation, and you basically want to provide guarantees that you are within a certain distance from a correct answer. And they use this Drawer-White scheme with truncation, and they basically prove under which condition this truncation, where to put truncation to provide guarantees on accuracy. That's roughly the idea. And that's also very tough. This is empirical, so it's not that difficult. I don't think they have to, but this is very dense in terms of mathematics behind. Okay, so that's Drawer-White's story. Now let me jump to another story. I'll probably comment a little bit later when I will be summarizing all the different schemes. I already mentioned that when I saw it first time, I thought that it should be related to this loop calculus, and it's certainly related to belief propagation because, well, if this computation, if this, there is interpretation of belief propagation in terms of infinite tree, and infinite tree, this self-avoiding tree is a part of infinite tree. So to a degree, it's an interesting statement that if you consider this infinite tree, you're getting, and you do computation on infinite tree, you're getting not exact result, but belief propagation result. So that's a statement. Now, however, if you truncate it in a, not truncate it, you basically cut it in a self-avoiding way and put particular values on the end, then you get exact. So it's kind of a little bit unusual, but it's certainly related to belief propagation. And we still don't know, I still don't know how it is related, if at all, to loop calculus. It's another construction, the way I see it. And of course, there is an interesting question of if they may be used together. Still don't know. So now let me turn to another one, which is to a degree was motivated by our loop calculus, but it's also deviated in an interesting, very different way, and it's by Max Welling. So Max was at Irvine, and now he's in Amsterdam. And Andrew Delfant is his former student, and Alex Eiler, he is professor at Irvine. So what they did, they developed a technique which is actually inspired by something which is rather famous and known, well, as a Japanese cluster expansion, or Kubo, because all authors originally inventing it in, well, 60s, 80s, the Japanese, not Marita, that's misspelled. Yeah, so, but that's what I wanted to explain. There is also a relation to certain literature in information theory, computer science, and those are references. And yeah, so another good subject for projects. So now let me illustrate it, the scheme, instead of explaining it in details. An example, but first let me also tell you that, and not explain details, but tell you that proofs behind this scheme. So I'll not be proving, I'll not be explaining details of why it is correct scheme, which I'll turn next. But proof is based on this reparameterization formulation by one, Wright, and others, and that's what we've been already discussing. So expression of partition function as an expectation of a certain expression given through gauges, but then those gauges, well, this is expression for arbitrary gauges, but if you enforce consistency, more or less gauges becomes as belief propagation gauges. So those B's are beliefs, so it's the same beliefs which I was using before. Yeah, so this cumulant expansion more or less follows from reparameterization version of loop series, which in the binary pairwise case is exactly the same as our loop series, but in general it is a little bit different. And this little difference is actually also interesting by itself for analysis. Yeah, so actually at this website, well, not only that, but also these courses, I put not only those slides, but some notes, and there are more details on this approach in the notes. And of course, there is the original paper, but it uses, of Welling and others, but it uses some other notations, and it's, I don't know, those are two different approaches to a degree. So let me walk you through that. It's actually, yeah, in our loop series, we have this, for this example, the generalized loop. So those are contributions. So motivation for Max and others was I'm trying to explain intuition. Well, even for the simple graphs, there are quite a lot of those. And if you start looking at those different contributions, there are some which you probably you would think you can get rid. And to a degree, this cumulative expansion reduces number of contribution to less number of terms, but it's not reduces in a certain sense. And I'll explain in which sense. But I don't know if you can see it in here. Let me maybe draw. Just try to clarify what kind of contributions we want to clearly we want to keep. So in this graph, let me redraw it again without coloring. We can clearly introduce those single connected structures, which are of this type, which are called here vertex loops. So vertex loops, they're not generalized loops, and well, some definition is explained here, but it's probably easier just to draw it. So will be those will be vertex loops, and the square is this part. And then what else? And finally, this one. Okay, so now I define those structures in terms of a set of vertices, and I require that all vertices from a set they define subgraph of my original graph, and all edges between those vertices which are in a set contribute to these structures. And this is simply object of this type, this is object of that type, all of them. However, for example, if I'll get rid of this edge, well, this object is not, I'm not counting in this vertex loops as vertex loop, because there is, well, again, this vertex loops is originally explained, you first fix a set of nodes, and then you require that all nodes which are in a set, if they have edge in the original graph, this edge belongs to this to the structure. And when I ignore this this edge, I basically violate the rule. So our generalized loops, there are more of them, and definition of generalized loops were in terms of, well, basically it was more about edges, right? So generalized loops are structures such that, subgraphs such that each vertex have at least two edges within the structure emanating from this vertex. And story is that every vertex loops contain at least one generalized loop, but generally more than one. Okay, so now let's see what kind of formulas, what kind of expressions you can get. So this cumulant expansion is stated in terms of this Z, which are partial partition functions. So those are objects for subgraphs. And then there are the C's, which they call cumulants after Kubo. And all those 1, 2, 3, 4, 5, 6 structures in this example, they're put in hierarchy. And this hierarchy has 3 levels. So there is this simplest structures, so the single connected loops, 1, 2, 3. Then there are structures of the second level, and then there is my original graph. So ZA is more or less partition function, which I want to compute. All others are auxiliary characteristics. And more or less, there is this relatively simple, straightforward algebra, which relates, well, first you define, well, you can do it in different ways. There are relations between the log of partition function and cumulants. So cumulants to a degree, at least for lowest level, for this level, cumulants are defined as just logs of respective partition function. But then there is this very straightforward algebraic relations between logs of partition function of a more complicated object. So for the second level, this log of ZBA is basically sum of cumulants which contribute to this B1. Contribute in the sense that there are two childs of this graph, right? Within this family. And you just put a full sum of all cumulants which contribute to this graph. And the same for this highest member of hierarchy, which is basically our full graph. In this case, we have only 3 levels of hierarchy. So that's, well, you can think of either of the two formulations as one of them is definition, another following, but they are fully consistent. So you can then invert it, and they call it Möbius inversion. Well, it's just a set of linear relations, so it's straightforward to invert. Here, all pluses on the right, and here there are pluses and minuses, and there is very direct and simple rule of which is plus and which is minus. So this is description of, if you wish, a computational procedure, but without truncation, it is still difficult and complicated. So in which sense it is a computational procedure? So this, if you, well, we want to compute this ZA. So what you do, you potentially compute cumulants. You start from cumulants and you go to ZA. But cumulants, well, to a degree, before truncation, it's just set of relations, and I don't think it has a computational meaning. But idea is that cumulants represent loops. If you would not have loops, you would not have those cumulants. And cumulants associated with loops which are high in hierarchy hopefully are less significant than loops which are low in hierarchy. So that's assumption. This actually was in a Kubo original approach where, again, idea, kind of very physical idea, not mathematical, kind of intuitive. If the longer those loops, the more complicated loops, the less significant they are, the respective cumulants. Truncation, which follows, which was suggested in this paper, they're more or less truncation of higher order cumulants. And that's what makes it computational schemes, the way I understood it. So, for example, there is this simplest possible truncation. You just ignore cumulant of the highest order associated with this big graph, and then you more or less do the following. You compute those partition functions for objects at the lowest level explicitly. Because explicitly in the sense that you sum, really compute it as a sum. Because those are well-defined small graphs, and you assume that you can do that. It's the simplest, partial truncation. You need to do computation of those z's for C1, C2, C3, B1, and B2. But still it is easier than computing partition function for the larger C. And then, because you ignore this cumulant, this CA, so this formula immediately relate your partition function to low order cumulants, and low order cumulants can be reconstructed from those two formulas, from this partial partition function. So this is roughly an idea. That's a little bit more dramatic, of course less accurate, when you basically force cumulants from all these hierarchies to be zero. in this paper, they provided this scheme. So those relations are exact. And those relations they prove, and they prove it with this reparameterization. It's actually a non-trivial part of the proof is to show that there are no other contributions from other terms. And that's, I mean, non-trivial part, and there are a number of theorems in this paper. But otherwise, truncation, they didn't justify it mathematically, but they experiment with it empirically, and considering rather big graphs and claiming success empirically for rather wide class of models. So the deeper your truncation, less you truncate, more accurate your answer you get. Yeah, so that's this paper, and that's another good subject for project, which maybe one of you can pick. Okay, so now another interesting subject, and probably will be, well, in this case, I guess I'm giving practically all details because this is really, if you wish, empirical work. Empirical, well, there is a nice construction, very straightforward construction, which I hopefully explain, and then there is a certain, why this construction is any good. There is no proofs, and there are actually quite a lot of open questions about this approach. But that's how many of the stories in this business started. So probably will be some proofs, but I am not aware of really strong ones. And some exception, but I'll mention these exceptions. Okay, so what do we do? So this is the same ID model, by the way, named in some community for this is a pairwise random Markov random field. Right? It's actually machine learning. Sometimes they use this term instead of ID. And again, it's actually easier to explain it on an example. And by the way, this example I just copied it from this paper, from original paper, Edith Freeman-Weiss, one which has a lot of citations. It actually started a lot of belief propagation discussions. So we consider this graph. So there are 9 nodes, and okay, let me start from standard belief propagation. What would we do for belief propagation in this case? In belief propagation, we would do the following. It's actually this factorization of beliefs, which is like what I wrote in here, but for this particular model, it would look like that. So you, let me maybe start drawing parallel on the left. So what would we do? Well, because of this form of factorization, right? So we have a pairwise factorization. Again, variables are on nodes, and factors are on edges. So, and those factors are with energies associated with edges. Therefore, very natural object for because of this factorization is this pairwise beliefs, right? So belief which is associated with edge, and for example, for this H12, that's what I wrote in here. So B12, which depends on X1 and X2. This is this pairwise beliefs. And then, remember this idea of interpreting BP as a correction to mean field. So first, I forgot what is, this correction will be coming in the denominator. I first care about denominator as I would be doing in the field. And natural object again pairwise, so I just take product of pairwise beliefs over all edges. And of course I didn't write them all down, but there are all these edges, 1, 2, and all the way to 8, 9, whatever number of edges are there. But then we discover that every vertex, oh, not every, but all vertices are overcounted. For example, this vertex entered in 2 objects, right? 1, 2, and 1, 4. And therefore, but I wanted that's kind of intuitive way of counting. I mean, what should I put in the denominator in the belief propagation factorization? So I put it b1 x1 in the power 1 because I had it represented through two edges, and I wanted it to be represented by ones. So I correct for this mismatch of mean field, putting in denominator b1 x1. Actually, in this representation for, let's say, vertex number 2, it enters in a 3 edges, right? Because degree is 3. So I overcounted by 2 because I wanted only once. So that's why I have squared in here, etc. So actually, vertex which, I didn't put it over there, so it's somewhere in those dots. But this vertex will enter 1, 2, 3, 4. So for this B, I should put power 3. That would be standard belief propagation. So now, idea is to extend hierarchy. So naturally, I have this pairwise object, and because I overcounted, I went down in the hierarchy, right? So I went from pairwise objects to individual objects. And it is, well, approximation in OOP case, as we know. And idea is, let's extend. Let's introduce objects of a higher order. And in particular, well, so one suggestion, there is of course freedom in how you choose it, but they suggest to just to illustrate, to choose those faces of this graph. So, well, faces is what is inside those big circles, right? So there is 1, 2, 3, 4. And it is everything which surrounds this 1, 2, 4, 5. That's what is shown here. So there are 4 objects of a higher hierarchy. And then, in generalized belief propagation, the idea is you start from so you build this hierarchy. And in this case, in the belief propagation, you have just 2 levels of hierarchy. We have pairwise objects and individual objects. In this new structure, we have 3 levels of hierarchy. Faces, edges, and then nodes. And I start from the highest level of hierarchy. I, again, first do like mean field, but on the level of highest level. Taking product of most complicated objects, right? And there are 4 of them. So it's 1, 2, 4, 5 for this object, for this object, for this object, for that object. So there will be product of 4. And then I go to next level of hierarchy. And just check how many times, if I overcount it or not. So this edge, and the next level of hierarchy are edges. So this edge only enters in one big, they actually call it regions, I believe here, regions. Enter one big region. So therefore I didn't overcount it, I didn't need to put a correction. But let's say this edge, 2, 5, it enters in 2, so it's in intersection of 2 regions of a highest level of hierarchy. So therefore I counted twice, I need to correct, that's why B25 is in here. So corrections therefore will be for that, for this, for those 4 edges only. And after that, you go to the lowest level of hierarchy, which are vertices, and now check if there is overcounting or not for each individual vertex. So this vertex, well, it's actually easier to see in this, what they call region graph. Basically, each vertex, as you can see, enters only once. So therefore, there is no overcounting. So let's check. So this B1, 2, 4, 5 contains 1, but no other from this highest level, which I introduced here, contains x1. And those edges, I didn't put this edge, right? So there is no dependence on x1. So therefore, I'm good with x1. It's only counted once. And when you go through this example, you'll discover that only X5 guy in the center, there is some problem with it, and actually, interestingly enough, it's not in the denominator, it's in the correction should be denominator. Let's see why. Because, because 5 enters in 4 regions of a highest hierarchy, number 4, right? 4 times. Then there are 1, 2, 3, 4 edges, and they're all which I put in the denominator. And therefore 4 by 4, so I have 0, but I need to count it once, so that's why I put it in the denominator. Yeah, so it's a plus or minus counting, and it's rather straightforward. So now it's very empirical in the sense that you can introduce those hierarchies, and you can hope that the further when you go from, let's say, belief propagation to generalized belief propagation, as I explained, you're getting better approximation. So empirically, we know that this is correct. My understanding is that there are no proofs of that for any of these constructions, and at least I'm not aware of. And just, showing that would be really nice for well, in a more general case, the more general the better. What we know, however, is that if we go to hierarchy, which will involve the entire graph, we're more or less done. And there is no point, of course, in doing that, right? So here, if I would go a bit further and would include the entire graph, yes, I'll get exact, and that's I can, of course, show, but I don't want to go. I want to approach as close as possible to factorize my joint probability distribution and, of course, approximate partition function later on as accurately as possible, but not going to hierarchy where the whole graph is present. So you probably see some reminiscence with this cumulant expansion. Actually, cumulant expansion come next after this paper, and they kind of, in some arguments, they put, of course, a lot of references to that. But yeah, so there are quite a lot of open problems. Of course, I didn't emphasize here that this is factorization, and you get your generalized beta free energy in absolutely the same way as I was getting it for belief propagation, but as Yedidi, Freeman, Weiss were getting. So there is this Kublai-Leibler comparison of measures stated in terms of general BX, right, exact, and then you substitute ansatz, and in the belief propagation case, this was the ansatz, and beta free energy, which followed from this ansatz, that's what we got, and here will be ansatz for generalized BP. So of course, again, it will depend on the particular choice of those regions and number of hierarchies. Yeah, so that's probably most. So there are a lot of empirical claims of success, and there is very little. Well, I don't think there are any results for partition function. However, there are some results, and rather powerful for, well, to a degree powerful, but still with a lot of open questions, towards this maximum likelihood version. And then remember, for belief propagation, well, you remember this story of LP relaxations, which I started to, very briefly and not systematically mentioned 2 days ago, but today we started lecture from that. You can very much directly extend this logic of relaxation to generalized belief propagation. And in this particular case, you can prove that when you add clusters, when you add hierarchies, you certainly will not lose an approximation. Belief propagation gives low bound. You potentially have a gap between this LPBP and exact, and when you add hierarchies, you're getting smaller and smaller gap. Unfortunately, we don't have a good way to control this gap. So if somebody would come up with a well, proofs or arguments, I guess more interesting would be to get proofs. When you you can show that maybe for some class of models you systematically close it, and not just, I mean, by little, but by some. Well, basically, if you'll be able, if somebody will be able to provide this approximate deterministic scheme based on generalized belief propagation, well, LP-GBP, that would be great. I didn't see it done. And it's probably not possible in general, but for some class of models, I feel that it's possible. Relevant leads two PhD theses, both from MIT, Jason Johnson and David Sontag, well, a few years apart, and they're actually both online, and it's rather interesting reading, especially in the David, well, because he came later. Well, some of you probably know the Shirley-Adams hierarchy in relaxations, in linear programming relaxation. So it appears to be very much related to this LP-GBP story, and well, it's very interesting, but rather mathematical subjects. And again, it's very, very good subject for discussion if somebody will want to. Okay, so I'm getting closer to finish line. So, well, will be basically one very brief example and conclusions, and we will be done. All right. So there is, well, I really forgot to mention this computational tree things, which probably would belong to this story, to this line of arguments too. But it's good that I recall when I was preparing this GPT, this junction tree. Actually, those slides are also from the C.D. Freeman Weiss paper. I recall it because I just reread this paper. So junction tree is an approach which actually reduces your graph to tree, but reduces it to by more or less collapsing variables and introducing objects with a high alphabet, just combining variables. And well, there are multiple illustrations. If you Google junction tree, you'll probably get. It's actually a rather well-known approach, and it was known certainly way before E.D. Freeman Weiss. I don't know when exactly. Probably roughly time of dynamic programming. But procedures are roughly like that. So if you have again this pairwise, like Eisen type of model on this graph, so first thing you do, you want to triangulate. You introduce fictitious edges with basically zero weight, but it's kind of important for construction. And then you collapse all those triangles, and they of course form a linear structure, right? And what collapsing means is that you introduce this variable, which now, well, if those three variables, if they're all binary, then alphabet for this new variable will be 2 in the power c, 8. And then you introduce another 3 variables and another 3 variables, and of course they overlap. And to account for this overlap, you introduce this, well, I think they call it separators. So those are called cliques, and those are separators. And this structure is already tree, and you really can apply this dynamic programming with belief propagation to the structure. And of course, you'll get all difficulties of computing stuff in the original graph because, well, there is no free lunch. Size of those clusters to get tree in general will be large. Well, in this case, it's not that big, but in general, it will be exponential. However, this is exact, and well, back in, I don't know, 70s or 80s, people developed some, I mean, some special, well, some rather straightforward algorithm for special type of structures, like maybe planar structures, maybe, well, when you have a street and there is something which is quasi one-dimensional, you basically introduce this reach variables, and you're more or less done. You're getting tree. So this is, I think that's very straightforward, simple, but I put it just for completeness. And I'll probably, I don't know if I'll get time, but I'll probably put in the slides this computational tree story, at least some reference, because it really also belongs to this part. And oh, I have another one which I forgot. Okay, let me mention this one. Actually, so yeah. Okay, so it's called graph covers. And it was introduced by Pascal Van Tobel and Ralph Cotter. Ralph Cotter unfortunately died. He was a brilliant information theorist. And then Pascal continued it himself, and actually most interesting results he got by himself in 2010. And it's another type of very strange result, which when I first time heard, I kind of didn't believe it, and then and it's still not clear in full to me how to use it, even though there are some interesting follow-up papers by Nicholas Rossi. So, okay, what is the statement? First of all, what is the construction? And actually, they built it first for error correction codes, but then more or less generalized to many other graphical problems. So, first you construct what they call covers. And covers, you're getting them in the following way. You have your original graph, and in this particular case, I think you can do it for all those graphical models of different type, and I think this is more or less for Ising model. You introduce replicas and M replicas, and well, some of the statements will be even about M going to infinity, so a lot of replicas, and then you consider, you start, okay, so if I have, maybe I'll do it, if I have, well, this particular graph, let me go. And then I introduce a replica of the same graph. So let's say 1, 2, 3, 4. 1, 2, 3, 4. What they call cover is when you take 1 and connect it to 4, for example, but not necessarily from your original replica, but maybe from another replica. And then, right, and of course there are multiple, yeah, and in this case, if you connect this one to 4 here, then of course edge from another replica should go backwards. But there are of course many options when you have a big, many replicas. Or covers of favorites. There are many covers, right? Many covers. And, well, motivation for them in error correction business, basically, this LP decoding or LPBP on covers can be interpreted, well, there is some interpretation of this bad cases of LPBP when you're getting not integer solutions in terms of integers on the covers. But then Pascal Van Tobel get to this remarkable statement, which I put in here, which also establish a relation between exact and belief propagation through covers. But it's a very strange relation. Honestly, I still don't understand it in full. I don't have much of intuition in that. So its statement is in here. So if you take exact partition function on any cover of size m, and then you, well, those averages, you average over all covers of this order. Okay, so you fix m. M is a cover. Well, this is 2 cover. You have m covers. You fix m. You consider all possible covers. For each cover, you have well-defined graphical model. You compute partition function for this graphical model. And then you average over all covers. Average means that you put equal weight, you just compute. You do it for all covers. Of course, we're not talking about practical, it's just formula, but interesting for us. And then you take square root of m's order, and then you are taking this limit, m going to infinity. And the statement is that you are getting belief propagation. you're getting what you would get for partition function computed under belief propagation. So it's kind of, when I first time saw it and I kind of misread, I thought it's in another order. So it's like I do something with belief propagation and I'm getting exact, and I thought that it's similar, it sounds similar to what. But having in this order, first of all, I don't know how to use it practically. I mean, for computations, really don't know. But in any case, so there is a statement, a theorem, and interesting project. What Nicholas Roisi did, and I also don't understand that in details, and actually would be great if somebody will pick it up and then we'll hopefully understand together. So he used this expression, or this relation, to prove the partition function of BP gives low bound for some class of models, and specifically for this pairwise log supermodel. It actually was not known in full generality, so in this sense it is new result, and well, proof based on this rather remarkable graph cover story. I don't know, well, actually this year Pascal put paper on something about two covers and actually linked to loop series. I didn't read it yet. It's another actually interesting project, potentially would be, well, there is a feeling that all those different techniques are either related or complementing each other. That's actually my last slide. That's what I wanted to say. So it's kind of on the level of speculations. In all those, well, in this last lecture, so in the first lecture I was talking about loop series or loop columns, right? And over there I didn't change graph, I played with factors. And I showed some interesting relations between BP and exact. Then this cumulant expansion to a degree extended on that, so it also didn't change graph, but use the same belief propagation gauges, but basically reshuffle those contributions in a potentially useful way. So there are all those loop calculus and cumulant expansion which are based on gauge transformations. Gauge transformations do not change graph, but change those factors, right? And then there are all those other self-avoiding tree, generalized belief propagation, graph cover approaches. They change graph. They didn't change factors, but change graph. So graphical transformation give factor functions, but modify the graph. Well, and what I can say is that they seems to be complementary. So they are not like one follows from another. So we don't see it. There is no reason for that. And therefore, conclusion is that it may be advantageous to build an approach algorithm combining. Actually, didn't see it much. I don't think I see it at all. Some papers which try to combine those two complementary techniques: modification of graph and modification of gadget. And actually, maybe one thing to add is that maybe there is some technique which kind of combines them in one. Well, maybe there is a way to generalize those gauges which allow interpretation for graph modifications. That's pretty much possible, but I don't know. And yeah, so I'm done for today. And so on Saturday, so it will be at 7. Right, there will be 2 lectures, and first lecture will be devoted to, again, and I'll be mainly discussing loop series, and actually not only, but I certainly will be focusing on specialized models. Well, if you look at it, well, there will be a story which is actually very remarkable. It's not, it's, well, 20 years old, from Francis Barahona, but even before from actually quite a line of physicists, even Feynman contributed to that. It's about Lamp graphical models which are easy because partition function is reduced to determinant. Then it will be a story of computation of permanent, kind of, with the help of loop series, story of minimum matching, and we also have a very, very nice way of using, not exactly loop series, and actually this is optimization problem, but completely closing this gap in a, not exactly an LPBP case, but with the use of belief propagation. And then Gaussian graphical models. That's a story with continuous alphabet. And in in the last lecture, the second hour, what I plan doing, I plan discussing some, very briefly, some problems which are, well, from my point of view of interest, but by no means solved. So it will be more like open problem type of presentations, the way I see it. And I also plan to agree with those of you who wants to participate in this project part. Well, maybe start discussing projects. We don't need to finalize it on Saturday, but at least, yeah. So I'll give you a list which I think a good subject, and I welcome very much your suggestions of what you would like to discuss, to focus. It may be either reviewing some paper and discussing it in a group, or maybe doing some independent research. I mean, maybe there are multiple options. So let's discuss it on Saturday. Okay? Thank you.
Misha, memorize the lecture at 5, not at 7.
Oh, at 5.
Yeah.
Sorry.